Welcome to the ePathshala lecture series in computer science. We are going to deal with the topic on computer architecture. So, the first module is on introduction to the course. So, the objectives of this module are to understand the importance of studying computer architecture, indicate the basic components and working of the traditional von Neumann architecture, discuss the different types of computer systems that are present today and the types of parallelism that exist among them and how to handle those parallelisms. So, first of all, let us look at why we should study this course at all. Why study computer architecture? First and foremost, it is an exciting subject. You find many interesting facts that are thrown open to you and you will find it a very interesting course. Any computer engineer or scientist should basically know the underlying details of the machine he or she is going to use. You may be an application programmer, you may be a compiler writer, whoever it is, if you know the underlying architecture, then you will be able to use the machine much more effectively and your performance will also improve. To become an expert on computer hardware, you need to know the underlying concepts of computer architecture. Also, to become a computer system designer, you definitely need to know the internals. Even if you are only looking at becoming a software designer, you need to understand the internals of the machine in order to improve the code performance. Also, to explore new opportunities, you need to be updated about the latest technological improvements that are happening. Only if you know the latest technological improvements, you will be able to apply those technological improvements, you will be able to use those, exploit those technological improvements to your advantage. And you know that it has an impact on all fields of engineering and science because computers are present everywhere, and whatever field of engineering and science you are at, you know that computers are very predominantly used, and this study on computer architecture will be very useful in order to use your machine more effectively. Now, what is a computer? By definition, a computer is a sophisticated electronic calculating machine that accepts input information. It processes the information according to a list of externally stored instructions and finally produces the resulting output information. If you look at the functions performed by a computer based on whatever operations it does, it accepts the information first of all. So, you need to have some functional unit which will accept the information to be processed as input. It stores a list of instructions to process the information. It processes the information according to the list of instructions that you have stored and finally provides the result of the processing as output. Now, based on the functions that we have identified for any digital computer, you also talk about different classical components of a digital computer. Now, first of all, we saw that you need to get input information, you need to process the information and then you need to output the information. You should also have provision to store the instructions as well as data. Now, when you talk about the 5 classical components of a digital computer, you talk about a data path. The data path is the path through which your information flows, the data flows. So, you have an arithmetic and logical unit called the ALU, which includes functional units like adders, subtractors, multipliers, shifters, etc. And you also have registers which are used as storage media within the processor, because the data has to be stored somewhere for processing. So, you need to look at registers which are inbuilt storage mechanisms available within the processor, and the ALU which is used for performing all arithmetic and logical operations. Now, this forms the data path of your machine. Now, if you look at the control path, you need to have some unit which will coordinate the activities of the various units. You should know when data should flow from one point to another point, when an addition operation has to take place, when a subtraction operation has to take place, so on and so forth. So, you need to have a control path. So, the control path coordinates the activities of the various units of the computer system, and the data path and the control path put together is called the central processing unit, or popularly abbreviated as the CPU. So, the CPU consists of the arithmetic and logical unit, the ALU. It consists of some registers which are used for storage, and it also consists of the control unit, which forms the heart of the computer system and coordinates the activities of the various functional units of the computer system. Now, all this put together is normally called the central processing unit. So, this has been depicted pictorially here. So, the 5 classic components of a digital computer. So, you have the processor shown in green, in the middle you have the processor shown in green, that is the central processing unit, which consists of your control unit. It has the ALU and it has storage. You have the memory unit, which stores all the information that is required for processing. So, it stores the data as well as the program. Program is nothing but a list of instructions. All of you all know that a digital computer is only a dumb machine. It works according to the instructions that are given to it. If you instruct it to add, it will add. If you instruct it to shift, it will shift. So, you need to have instructions given to the processor. These instructions as well as the data on which these instructions will have to operate on will have to be stored somewhere, and that storage is what is called your memory. And you have your central processing unit, which consists of the control unit and the ALU, which is responsible for executing the stored program from memory. So, initially the program is stored in memory, you take the instructions from there, you execute them, and then you have and when an instruction instructs you to do some arithmetic or logical operation, you have the ALU which does the arithmetic operations or logical operations as requested by the program. And your input output unit is basically for communication purposes. So, you need to feed your instructions as well as data into memory. So, you need an input unit for it. Similarly, you need to take out the result and display the result to the outside world, communicate the result to the outside world. For that you need an output unit. So, the communication with the outside world can be done with devices like a monitor, a keyboard, or different types of storage devices. Now, apart from these classical components, every machine typically has a network component for communication with other machines. So, we know that it is most of the machines these days we do not operate them only as a standalone machine. We need to communicate from one machine to another machine, either within a very short distance or across the globe you may have to communicate with other machines. So, you definitely need to have communication from one machine to another machine. So, you definitely have to have a networking component which is used to communicate within the various machines. Now, having looked at the functional components of a digital computer, having identified the basic components of a digital computer, now what is it that we are going to study in this course on computer architecture? I pointed out that computer architecture is an exciting course and is important for everybody. We have also identified the classical components of a digital computer. Now, what is it that goes into this course on computer architecture? When you look at computer architecture, we say computer architecture composes of computer organization plus the instruction set architecture. Now, what you mean by the instruction set architecture, or what is abbreviated as ISA, is what the computer does. It is a logical view of what the computer is capable of doing. And when you look at computer organization, it basically talks about how the ISA is implemented. So, which gives you a physical view of how whatever you have specified that the processor will do is actually getting implemented. So, basically we give a specification here, we say these are the things that the machine is capable of doing, that is specified in your instruction set architecture, and how it actually gets implemented gives you the computer organization part. So, both these put together is normally called computer architecture, and in this course we are trying to cover both the computer organization part as well as the ISA part. Now, what are instructions? We have been talking about instructions, we have been talking about data. Now, what do you mean by instructions? Instructions basically specify commands to either transfer information from one point to another within a computer. Say for example, we have looked at different classical components of the processor. We looked at an ALU, we looked at a memory, we looked at storage units like registers, etc. So, you may have to transfer information from one register to another register. You may have to transfer information from a register to a memory location to a register, or an input output device to a register. So, all these types of transfers will have to happen. Now, how is this going to happen? So, you will have specific instructions which will say transfer the information from this source to this destination. So, instructions basically specify commands to either transfer information from one point to another within a computer. It may be transfer of information between the computer and the I/O devices. So, it is not necessarily between registers and memory or between registers themselves. It may also be transfers from I/O locations or I/O devices to computers. You may have instructions which will instruct the computer to perform arithmetic and logical operations like multiply these two numbers, add these two numbers, and these two numbers, shift right this number by so many bits. So, all those are instructions which will tell the computer what arithmetic logical operations to do. And apart from this, it is not just enough if you can transfer information from one point to another and instruct what operation is to be done and store it in some place, but you also have to have some instructions which will control the flow of the program. Say for example, I am trying to add two numbers. If the result is greater than something, I want to take one course of action. If the result is less than something, I want to take a different course of action. So, you need to have some instructions which will allow you to control the flow of the program. So, you need to have instructions which are specifically used for that. So, such instructions like jump, I may jump from one point to another, or may have a subroutine call. Subroutine call is a function call. So, you write modular programming. So, when you are executing something, I need to specifically go to a point, execute a function, get the result, and then continue with my main program. So, all these instructions are examples of control flow instructions. So, you need to have instructions to specify all this. And once you have these instructions, now all these instructions, you put some of these instructions in a sequence. So, a sequence of instructions to perform a particular task is called a program, and which is stored in memory. Say for example, if I have to add two numbers. So, what you will have to say is initially those two numbers, let me say those two numbers are stored in memory. So, from memory you will have to bring them to the arithmetic and logical unit, specifically the adder, to add those numbers. So, you will have to first of all give data transfer instructions to transfer these two data from memory to your adder, instruct the adder to perform an addition operation, and if you want to put the result back in memory, then you will have to again use data transfer instructions. So, store the result from your registers or from the adder unit to your memory location. So, whatever task you need to perform, you need to have a sequence of instructions that need to be written to perform the task, and that is basically what is called a program. And what the processor does is, the processor fetches instructions that make up a program from the memory and performs the operations stated in those instructions exactly in that order. So, suppose if you have a control flow instruction in between and it says do not execute the next instruction, but jump to some other location and execute that instruction, it will again jump to that point. So, whatever is specified in your sequence of instructions is exactly executed by the processor. And now, once we know what these instructions are, get at least a rough idea of what these instructions are, we also need to know on what data will these instructions operate on. So, we talk about data. Data are the operands upon which these instructions operate. Now, the data could be numbers, it can be decimal numbers, it can be binary numbers, it can be octal numbers, whatever it is, and or the data can be encoded characters. Data in a broad sense means any digital information, and computers use data that is encoded as a string of binary digits called bits. Now, if you look at the memory unit, the memory unit stores instructions as well as data as a sequence of bits. An instruction is also encoded as a sequence of bits, a data is also encoded as a sequence of bits, and the processor reads instructions and reads and writes data from or to the memory during the execution of a program. Group of bits stored or retrieved at a time is normally called a word. The word length of the processor depends upon the processor that you are looking at. Suppose if it is an 8-bit processor, you talk about a word length of 8. If it is a 64-bit processor, you talk about a word length of 64. And the number of bits in a word is termed as the word length of a computer. Now, in order to read or write to and from memory, a processor should know where to look. A memory consists of a number of memory locations. You may have, say for example, if I am looking at a 1K memory, I may have 1024 memory locations there. Now, how do you identify which memory location to read from or write into? So, just like how we have unique addresses to identify our houses, each memory location has a unique address. So, in order to access a memory location, we need to know the unique address of the memory location, and the processor reads or writes to and from memory based on this memory address. A random access memory provides fixed access times independent of the location of the word, which is known as the memory access time. So, you normally define memory access time as the time that elapses between the initiation of a request and the satisfaction of the request. Say for example, I have put in a memory read request. So, the time between the requisition that has been put in and the time when the data actually arrives is called the memory access time. So, the memory access time depends upon the speed of the memory unit. A slow memory has larger access times, a fast memory has lower access times. Now, the memory and the processor which will have to communicate with each other in order to read and write information. So, in order to reduce the communication time, a small amount of RAM, normally known as the cache, is tightly coupled with the processor. And also modern computers have 3 or 4 levels of RAM units with different speeds and sizes. So, the fastest and the smallest in size is normally known as the cache, and the slowest and the largest in terms of density in terms of storage capacity is normally known as the main memory. Now, the primary storage is insufficient to store large amounts of data and programs. Though we look at a main memory which is very high these days, the main memory is not obviously enough to store all your programs and data. So, you need to look at secondary storage also. So, you look at secondary storages which are capable of storing large amounts of data. Examples are magnetic disks and tapes, optical disks, CD drives, and the access to the data stored in secondary storage is definitely slower, but you take advantage of the fact that some information may be accessed infrequently. And the cost of the memory unit obviously depends upon its access times. So, the closer the memory is to the processor, it is obviously going to be the fastest and it is going to be more expensive. Now, coming to the arithmetic and logical unit, the arithmetic and logical unit, as already pointed out, it is responsible for performing all your arithmetic and logical operations, and in order to execute an instruction, operands need to be brought to the ALU from the memory. So, we need instructions which will bring the operands from the memory to your ALU and perform the operation, and similarly the results of the operation are stored back in the memory or retained in the processor itself in the registers for immediate use. Now, if you look at the control unit, the operations of the input unit, the memory unit, the ALU and the output unit are all coordinated by the control unit. Instructions control what operations take place, whether it is a data transfer that has to take place or an ALU operation that has to take place. The control unit, in order to do these coordination activities, generates what are called timing signals which determine when a particular operation should take place. Now we have looked at the different functional units of a processor. How are these functional units connected together so that they can communicate among themselves? So, for a computer to achieve its operation, the functional units need to communicate with each other and they need to be connected with each other. The connection is done by means of a set of wires called a bus. So, the bus that has been shown here is responsible for establishing a connection between the various components of the processor. A bus is nothing but an interconnection of wires. So, if you are talking about an 8-bit bus, it will be capable of carrying 8 bits of information. Functional units, as I told you, is connected by means of a group of parallel wires called a bus, and each wire in a bus can transfer one bit of information, and the number of parallel wires in a bus is normally equal to the word length of a computer. Because when you talk about a processor which has a word length of say 64 bits, it means typically we are going to operate on 64 bits of data. So, it is only reasonable that we also have a bus which can transfer 64 bits of data from one point of the computer to another point of the computer. Now, having looked at the functional components, we look at what is meant by the traditional von Neumann architecture. Traditional architecture with the classic components mentioned earlier, which uses the concept of a stored program concept, is normally called a von Neumann architecture. What we mean by this is, instructions as well as data are stored in memory as sequence of zeros and ones, and the processor executes these instructions sequentially, and program flow is controlled or governed by the type of instructions and other factors like interrupts, etc. The fetch and execute cycle is repeated continuously. So, an instruction is fetched from memory, it is executed, and then you go ahead and fetch the next instruction from memory. So, this indicates the fetch execute cycle. So, first of all we do a fetch cycle where the instruction is being fetched from memory. So, you recollect that instructions are being stored in memory. So, you need to have the address of the instruction. Using the address of the instruction, go and fetch the instruction, then decode the instruction. Decode the instruction is, after all, it is a sequence of zeros and ones. So, you need to know what is to be done with those zeros and ones, whether it is an addition to be performed or what operation to be performed, where the operands are available. So, that entire information has to be decoded, which you will understand as we look at the instruction set architecture. And once you have understood where the operands are, you will have to fetch the operands, and once the operands have been fetched, you will have to go ahead with the execution of the instruction, perform an addition or subtraction or whatever operation, and then finally store the result. This is called the fetch executed cycle, which is done repeatedly in the case of a von Neumann architecture. This gives you an overall picture of a general computer system which follows the von Neumann architecture. Now, the advantages of the stored program concept is that programs can be simply shipped as files of binary numbers where you can maintain the binary compatibility, and computers can inherit ready-made software provided they are compatible with the existing ISA. This leads industry to align around a small number of ISAs. Now, when we look at computer organization, organization, as we pointed out earlier, is the realization of the instruction set architecture, and you will have to look at the characteristics of the principal components that make up your computer system. You will have to look at ways in which these computer systems are interconnected. You will have to find out how information flows between these components. You will have to look at what is meant by such information flow and how is this information flow actually controlled, and you will also have to have an RTL description of what is happening within the machine. Now, all this put together is what is called computer organization. So, as I already pointed out, we are looking at the ISA, which gives you the specification what the processor is capable of doing, and you have an organization which basically tells you how this gets implemented, and this is traditionally implemented on a von Neumann architecture, which repeatedly goes through a fetch execute cycle. So, this gives you again an overall picture of the Intel NetBurst microarchitecture, which gives you the different levels of caches, the fetch and decode unit, the retirement unit. You will understand, and the caches and all that. You will understand all these diagrams in a much better way as we proceed through the course. So, we have had a lot of technological improvements that has been happening. So, starting from 1951, from vacuum tubes, we went into transistors, ICs, VLSIs, ultrascale ICs, so on and so forth. And we find that the processor transistor counts have increased about 30 to 40% every year, thanks to Moore's law. Moore's law was basically proposed by Gordon Moore of Intel in 1965, and he proposed that the transistor densities are going to be doubled every 18 to 24 months, and that has really been holding good. The memory capacity also has gone up to about 60% per year, the disk capacity about 60% year, and you have opportunities. All these technological advancements have given rise to opportunities for new applications, and this has given rise to better organizations and designs. I have already pointed out Moore's law, and this shows the processor performance over the past 2 or 3 decades from 1978 to 2005. You find that after 2005 you find that the performance has actually slowed down by what is called the power problem and the memory latency problem. Now, before we look at more details of other components, we look at the classes of computer systems. You have different classes or different types of computer systems that are available. One is the desktop or notebook computers, where this is the most competitive market. You are looking at general purpose applications here, where you plan to run a lot of applications here, and main constraint is the cost performance trade off here. The next category of computer systems is your server systems, where they are network based. You need to have high capacity for them. Performance is very important for them. Reliability is very important. Reliability and availability are very important here, and it basically ranges from small servers to huge servers that are even building sized. The next class of computer systems is again an important classification, embedded systems, where the computers are hidden as components of other systems. For example, when you look at a mobile phone, you do not realize that it is a computer system, but you know that there are many processors inside your mobile phone. That is a classical example of an embedded system. A washing machine is a simple example of an embedded system. These embedded computers have a stringent power performance requirement, they have stringent cost constraints, and they are specifically meant for application specific performance. You have a processor which is meant to do a particular task, because unlike a desktop processor, you are not going to run a range of applications there. It is going to be meant to do a particular type of application. So, you expect it to perform well with respect to that particular application. And this is a class of computer system which covers a wide range. Your requirements may range from a very small toy car application to a very sophisticated diagnostic system, for example, or surveillance mechanism. So, depending on that, all your requirements are going to change. Last of all, you also have the personal mobile devices, which are very predominant today, where cost is important, energy is important, and media performance becomes very important for personal mobile devices. And personal mobile devices also will have to lay a lot of importance on the responsiveness. Once you put in a query to your PMD, you expect to get an answer immediately. So, the responsiveness is very important when you are looking at personal mobile devices. And of course, these days you also have clusters and warehouse scale computers, which are becoming very popular. So, you have a large number of computers put together and called a cluster or a warehouse scale computer. So, here again price performance becomes very important. Throughput is more important here. The number of transactions done per unit time, or the number of web services that have been serviced, all that becomes very important when you are looking at clusters. So, that is again the same as that of your servers, and energy proportionality also gains a lot of importance when you look at this type of computer system. So, having seen the different classes of computer systems, we will have to point out to what are the driving forces of computer design. So, the main driving forces of computer design, the primary constraints are energy and cost. Today, everybody is striving to design computer systems which will minimize your energy and cost. And also, we will have to look at the different types of parallelism that your applications exhibit and try to exploit this parallelism in the computer systems that we design. So, that becomes the primary driving force of a computer system. So, if you look at the different types of parallelism, programs may exhibit what are called data level parallelism and task level parallelism. So, when you try to exploit this parallelism, you have to bring in computer systems, design computer systems which will try to exploit this parallelism that is available in your programs. So, you need to look at exploiting data level parallelism. Task level parallelism is more independence. So, you can have different tasks of execution and you will have to exploit this. Instruction level parallelism is, if you look at different instructions in a program, if you find that instructions are independent of each other, can you try to look at executing these instructions independently, thus executing the instruction level parallelism. Thread level parallelism is exploited more in terms of task level parallelism, and when it is a more loosely coupled architecture, we call it a request level parallelism. So, applications exhibit different types of parallelism, and the computer hardware that you are designing should try to exploit that parallelism and try to give you better performance. So, in order to summarize whatever we did in this module, we first of all pointed out why you need to study computer architecture itself. So, the motivation for the course, what is it that you are going to study in this computer architecture course. So, and then we pointed out the functional units of a digital computer, how they are interconnected, what is meant by a traditional von Neumann architecture and what is meant by the fetch execute cycle. And last of all, we pointed out the different classes of computer systems and the driving forces that are driving us to come up with better and better computer architectures in order to exploit the parallelism that is available among the various applications and also bring down the energy and cost. Thank you.